So you missed lesson 3.2.4, which was all about boiling substances. And so let's talk about this introduction here. It says the polarity of molecules affects how they interact with each other. One way we can observe the attractions between molecules is by observing how much energy is required to change a sample of the substance from liquid to gas, which happens at the boiling point. A process called distillation is used to separate substances that are soluble in each other, but that have different boiling points. Distillation is often used to separate the compounds mixed together in crude oil in order to produce gasoline, plastic, and pharmaceuticals. So the first thing that it wants you to do is go into Odyssey and go to the applied chemistry area and take a look at the gasoline simulation. It wants us to find two similarities and two differences between the various components shown. It wants us to figure out which thing we think would have the highest boiling point and which component we predict would have the lowest boiling point. So let's take a look in Odyssey under Energy and Transportation, the gasoline. Now when we first look at this picture of gasoline, it kind of looks like it's made of a bunch of the same molecule, but if you read over on the right here, it says, the simulation cell on the left shows a sample of the liquid that is found in the fuel tank of a majority of cars. Except for certain additives, gasoline is very simple in that the basic constituents are all hydrocarbons. That's a compound that has nothing but carbon and hydrogen. But gasoline is, in a different sense, complex because there are 25 different kinds of these molecules. And we're going to take a look at those in a second. But first, if I spin this picture around and we look a little bit closer, we do see that not all of these molecules look the same. And there is a little place right here where you can actually click and slide through. So there was butane, which is 4 carbons in a row. There's pentane, 5 carbons. Hexane, 6 carbons. Heptane, 7 carbons. Octane, 8 carbons. There's methylbutane, which is 5 carbons, but they're not all in a straight line. There's 2-methylpentane, so now we have 6 carbons, but they're not all in a straight line. 2-methylhexane, very similar. I'm going to go through these a little bit faster. Lots of different hydrocarbons. Now here's one that has a ring called toluene, another ring called xylene, different isomers, and the last one here is cyclohexene. So there is a ring structure. So if we go back, what are some of the similarities and some of the differences? Well, they're all similar in that they have carbons and hydrogens only. Differences, they are different lengths and there are different isomers too. Which one of those do we think would have the highest boiling point? And which one would be the easiest to boil? Well, I'm going to say the largest one will be the hardest to boil. So it would have the highest boiling point. But at this point, I'm just guessing. So you can write your own predictions here. Let's take a look at the next part. So we're going to be, in class, we set this distillation apparatus up. And basically, we've got a hot plate, which we did put on a setting of 5, so about halfway. And then in this flask, we actually put this murky looking sample of, it was representing crude oil. And we were heating it, and what happened was things that turned into a gas would go up into the air. This is a thermometer here, so pretend that there's just these gas molecules. They go up into this little tube here. The hot gas molecules travel all the way through, and then they get here, and all of a sudden there's a whole bunch of really cold water in here, And so it travels through this tube, which is separate from the cold water, and this gas cools back into a liquid, and then it drops down into the beaker at the bottom. So each time that there was a liquid coming out, it was interesting because the boiling point was different with the thermometer. So we collected different samples. They're called fractions. So here were the steps that we went through. We put 15 milliliters of the oil, like I was saying, in the bottom of the flask, and we had everybody make a little prediction of what we thought the graph would look like of time versus temperature as you heat up your sample. So a lot of people in class draw a line like this. So as time goes on, the temperature keeps going up, up, and up of that crude oil. And I'll give you a little hint, that's not how it looks. And the instructions were keep collecting or keep heating until you collect what's called the first fraction. So let's put in some data here that you can use. At 30 seconds, it was about 22 degrees, 23, has a slow start typically till it starts gaining some momentum. As you can imagine, it's a little bit like watching grass grow while you're waiting for the sample to heat up. And it depends on the heat source too, how quickly things go up. Make this go a little bit faster. Maybe you turned up your hot plate. And then here, right at about 78 degrees, you can clearly notice that there are some bubbles forming. So it's something in that flask is starting to boil. And also the temperature really slows down. So we kept heating, and we noticed that some liquid now was coming into that beaker. So that is called fraction 1. Oops. And fraction 1 was a clear liquid, and it smelled like alcohol. And the boiling point was somewhere around 80 degrees Celsius. So then we kept heating, and the temperature kept jumping up, but it started to slow down as it got closer and closer to 100 degrees. So right around 99, 100, it kind of stayed put for a little while, and then it went back up. And then we didn't want the thermometers to blow up, so we had to stop. Oops, keep doing that, sorry. So fraction 2 was also clear, and it had a slight alcohol smell, probably from the first fraction. Oops, I'm giving things away here. If it has a boiling point at 100, you might guess what it is. No smell, boiling point around 100 degrees. And the third fraction was still like a brown color, also more viscous. No smell, and we don't know what the boiling point is, but we do know it's more than 100 degrees Celsius because it never came out of the flask. We would need different equipment to go above 100 degrees. Like I said, our thermometers could blow up. So then we had everyone draw each of these structures of what was in the flask. It was a mixture of water, ethanol, and glycerin. And we built each of these in Odyssey so that we could look at the polarity maps of each of these. Glycerin is interesting because it's got 3 different OH groups, one on each of the carbons. Add in my other carbons here. And so let's take a look at the polarity maps for each of these, and we'll actually go ahead and snip these in. So here's the polarity map for the H2O. So there's water's polarity map. I'm clicking on the snipping tool, and I'm going to put a copy of that in here. Make it smaller. And then let's get one. This is ethanol. You can see the 2 carbons in there, and there's still an oxygen. Let's get that into our table here. And finally, last but not least, let's get the glycerin picture in there. Oops, here we go. All right. This one was big. Okay, then we're going to do some ranking. We're going to rank these molecules based on their size, first of all. So it wants us to write in if it's small, medium, or large. It's pretty easy to see that water is the smallest here. Ethanol is medium, and glycerin is the largest. And then it asks us to describe which of these has the most polarity on the map, meaning the most red and blue. So if we take a look at this, it looks like water has the most red and blue. There's a big red section and a big blue section. So this would actually be the largest here. And the second largest, there's quite a bit of red and blue in the glycerin. So I'm going to rank this one medium. And then the ethanol has the smallest. Now it says list the substances in order of lowest to highest boiling point and use their combined ranks for size and polarity to make sense of this order. So the one that came out first, fraction 1, was definitely the ethanol. And water came out second. And then last, the thing that never came out was the glycerin. And if we combine these ranks, smallest and largest would make a medium. Smallest and medium would make a small medium. And largest and medium would make a medium large. So now if we put these in order, the smallest, if you combine those two forces, would be ethanol, water, and then the glycerin. So if we're making sense of this, we would say something like ethanol has the lowest boiling point because it is least polar and somewhat small. And then we could expand and say water is next highest for the boiling point because it is small but very polar. And finally, the glycerin has the highest boiling point because it is large and fairly polar. And then let's take a look at some of these check-in questions together. So when you are refining crude oil, what they do is they heat it up, and they have this even fancier equipment than we did, where they can basically separate out based on the temperature of the different hydrocarbons, and they can, depending on the boiling point of them, certain things will come out first. So just like we did today, only they're doing it with a mix of many, many more things. So first there's a term here. It says hydrocarbons. I want to clarify that that is literally a molecule of no double bonds. It's just a whole bunch of carbons and hydrogens. And sometimes it'll give you a range. I'm not going to draw this all out, but here it says C1 to C4 gases. So a C1 gas would just be CH4. And then a C2 gas would be C2H6. So you'll notice the next set is C5 to C9, and they get bigger and bigger and bigger and bigger as you go down. So none of these have the OH group that we were working with in our lab, but it's similar because size definitely plays a role in what is going to boil out first. So let's take a look at these questions. It says, what fraction of crude oil would you expect to be collected first? And you would definitely say the lightest ones. They're smaller. And we learned that that definitely plays a role. What fraction would you expect to have the highest boiling point? So here you would say the greater than 70 hydrocarbon, because that is the biggest. It's a little bit harder to boil something if the molecules are really large. You've got to separate them in order to turn them into a gas. Name one other property that you think would also change based on polarity and the length of the molecule. So you could say something like the melting point. That's definitely related. In a very similar way, you could say that things that are small are easier to melt. Than larger molecules. You could also say something that more polar molecules are harder to melt, just like they're harder to boil. And then here you're supposed to write out 3 questions that you've got about how this process of converting crude oil into the different fuels that we use works. And I think you can probably have a lot of questions based on this picture. Like, I want to know, what is naphtha and what chemicals is it used in? And then the homework questions you can work on your own, but they also involve graphing the data. And so this is really an exercise in Microsoft Excel. And I highly recommend that you do that using the data that was provided here. That's totally fine to use for this. So there you go. That's what you missed. You missed the excitement of the lab part, but hopefully this will make you feel a little bit caught up.